guys can remember if I finished. Okay, so we had those exceptions on the periodic table. Chromium, molybdenum, tungsten, and then copper, silver, gold. And so the stability of elements, the more stable, the less reactive. And stability is first determined by having full shells. Elements in which the shells are completely filled are the most stable elements. And so these are your noble gases. And of the shells, kind of remember that there is an overlap with the 4F, 5F, 3D, 4D, which they belong to that. And so that's becomes part. So that each one of these is a shell. So you have helium, neon, argon, krypton, so on and so forth. And so each one of those is the shell. Okay. And when that is full, you have the most stable elements, which are the less reactive noble gases. So helium, neon, argon are completely unreactive. There is absolutely no chemistry associated with these elements. There are no chemical reactions. Okay, and there's only a handful of chemical reactions for krypton and radioactive.
I have a question. So when you say shell, do you mean like for the 5 energy level, you mean like that it has to have all of the 5 energy level sub-levels filled?
Yes.
Okay.
Yes, it's the level NT. So for helium, the one is full. So for neon, all of this.
Mm-hmm.
Now, the assumption is that once we're here, whatever's below is already full.
Yeah.
Okay. So argon, first is full, second shell is full, third shell is full.
Okay.
And then krypton, first, second, third, fourth.
And
And
because
so-
I was just, I didn't know if you meant like if like the transition metals that have the 3D shell are the sub-level full, but they're still reactive. So that's
So
not.
that's actually the next one.
Okay.
So that's the first. Then if elements cannot achieve full shells, then full subshells is the next step. Now, the more electrons in a subshell, the more important that subshell becomes. Okay. And that kind of leads to copper, silver, and gold being exceptions. Because it's more stabilizing to fill a D shell with 10 electrons than it is to have a lens that's full with only 2. And that's why we have that electron jump from here to here. Okay. So within this full subshells, then a full D is more important than a full S. And that's the reason copper, silver, and gold transfer an S electron to the D, because then the D becomes full.
So like what I wrote for this is the forest shell has lower energy level than a 3D shell, so forest shell fills before 3D.
On the way, yes,
Same goes
So-
for 5D.
on the way up. In terms, and that's in terms of Huntsville.
Okay.
Okay. But as you start filling in those subshells,
So you're talking about those elements that have the exception, so instead of having a full S, they fill the D to make them more stable.
But this reasoning explains some of the other properties too. And reactivities that we'll see in the next chapter, why some elements will combine in particular. Now, so you do have the nucleus, okay, and then you have your protons here. Okay, so this is positive.
Oh, sorry.
And as you start filling in those shells, so the 4s shell only has 2 electrons, 2 negative charges, right? And then after that shell, and keep in mind that they're not circular, but you know, it makes a little bit more sense. You have the 3D here, but you can have a total of 10. So you put 1 electron, but for every electron that we're adding it because there's a corresponding proton. So another electron, there's another proton, electron, proton, electron, proton. So it's like a magnet. So the attraction between that 3D shell and that positive nucleus starts getting stronger and stronger the more electrons.
Oh.
Okay. Now the energy level is associated with how close we are to the nucleus. The closer we are, the lower the energy. The higher we are, the farther away from the nucleus, the higher the energy. Well, since this magnet, this attraction is getting stronger, it starts closing in, it starts shrinking. And at some point, it shrinks so much that it overtakes the 4s and now the 3ds below.
Wouldn't it have to, but wouldn't it?
So is
lose
that
some
why they're
energy?
transition? That's why you can, it matters the number of electrons, or what?
Oh, no, 'cause
Because that's how they add up, right? Because it could be, because when I was studying it, I was noting in the transitional shells, right?
Yes.
That's where it switches.
Yes.
Okay.
So
That's when you're adding and subtracting
when
the.
you're coming up with the electronic configurations,
Uh huh.
okay, then you fill in the 4s and then you start filling in the 3d. Okay. But as you get these electrons in, the 3d becomes lower in energy. It gets closer. And so there is an energy loss, if you want to look at it in terms, for the D shell, okay? And the 4s kind of remains at the same level. Because what's going to happen in the next chapter, when we start looking at ions, okay, most of the transition metals have a +2 charge as one of the choices. That's because they're losing 2 electrons. And the 2 electrons that are lost are not from the D section, they're from the S. So typically, the last electron you put in is the first one to come out.
Mm-hmm.
Not so for transition metals. Okay. The S are the ones to leave first before we start taking those metals.
Because the 3D has stronger energy.
Because it's further away.
Okay, makes sense.
Okay. Then the last level,
Thank you.
if we cannot have full sections, then have full. And this is functional, in which you maximize parallel space. Okay, so there's stability when electrons are spinning in the same direction. So that, for example, a P shell that has 3 electrons is lower in energy than one that has 4. Okay, because this now is canceling one of the parallel spins. Okay. And then same thing when you're on the D shell. So in the exceptions for chromium, molybdenum on that 4th column, okay, when this electron transfers over here, all of a sudden we go from 4 parallel spins to a total of 6. And that becomes more stabilizing, and that's why that electron moves in, And here, that instead of being at S2B4, we end up with an S1B5.
So that's why it says reactive.
And so you have, we take a set of rules to fill in, and then there's some exceptions, and on the way out, we end up noticing some of these. And so, in the next chapter, then electrons, it's in the atoms, are going to combine into molecules. And they're going to transfer and or share electrons in order to try to hit these different levels of stability.
What rule is that?
Hun.
Tons.
Hundred, H-U-N-D-S, the one with the parallel spins. And then the one where you start at the bottom and move your way up, that's the off buffers.
Was tons rule in the book? I don't remember reading that.
I saw it.
Was it-
I don't remember if they mention it by name,
Um,
but they do,
Oh, okay,
Tell
yeah, I
us.
remember those, it just, I didn't remember that it was tons rule.
I just can't remember if they, I know it mentions poly. But I don't think it mentions tons by name.
And
I
the
think it
principle,
just tells you. And it doesn't tell you why.
and the principle is the least reactive as you move up, or what? If
That
the principle that.
That the electrons go on the lowest energy orbital first.
First.
So that's what you do that would be order, that tells us this order.
Yeah. And that's the principle.
Alpha principles letting us know what this order is.
I just wondering how many people figure this, right?
How did they know to look at all of this?
Like mind baffling.
Okay.
I always wondered that. They didn't
So-
have
I know.
Positives and negative attraction.
I'm trying to feel like all this information is.
And the whole point. So valence electrons. Valence electrons are the electrons that are in the outermost shell. So, when the first shell is full, the elements on the second row of the periodic table. Okay, the first one is full, we call these core electrons. The ones that we're putting in here, these are the valence ones. And then we get to neon, and first and second is full. So now these become core. And as we start filling in the third row of the periodic table, then as we put those last electrons in, those are the valence ones. Okay, and then we get into argon, that's full, all of these become core. Now these become the valence ones.
That's what we know the group.
So they're the ones in the outermost energy level, basically the one that has the highest number there. Okay, the electrons that are in the highest shell by number, those are your valence electrons. For the representative elements, the first two columns, the S section, and the last six, the P section. Okay, the group number tells us how many valence electrons
In
there are.
F and P?
Hmm?
F and P, you said?
S and P.
S and P.
S and P. Okay. So as you look at the electronic configurations, group 1, they're all S1s. And then group 2, they're all S2s. And then we skip the transition and go all the way up to group 3. Now they're all S2P1s. 2 plus 1 is 3. 2 plus 1 is 3. 2 plus 1 is 3. So we're in group 3. Then group 4, S2P2. 2 plus 2 is 4. 2 plus 2 is 4. 2 plus 2 is 4. And then that pattern, S2P3, S2P4, S2P5, S2P6. So 2 plus 3 is 5. 2 plus 4 is 6. 2 plus 5 is 7. 2 plus 6 is 8. That's how many valence electrons there are, and that's the group number. So the group number matches the number of valence electrons.
Not too-
So we take a look here at sulfur. So sulfur's 1 is 2, 2 is 2, 2 is 2, 3, 4. So the first shell is full, second shell is full. Okay. So these electrons right here, they're the core. These right here, the 3 is the outermost. Okay, these are the betas. Right, they have the highest number. So the S&P electrons end up being the valence electrons. So for calcium's in the second column of the periodic table, fourth row. So it's period 4, group 2. The group number tells us the valence electron, so it has 2 valence electrons. And for calcium, all of this is full. And then we get to here, and there's 2 electrons there. And so those are the valence electrons. For lead, now we're in the 6th row of the periodic table. As we fill it in, it's 6s2, 4f14, 5d10, 6p2. Okay. Now, if we rearrange this by increasing shell number, then the 6 are the highest. And there's 4 electrons on that level. And lead is in group 4. So it has 4 valence electrons. Here, 4 valence. So if all you need is to know how many valence electrons, 1, 2, 3, 4, 5, 6, 7. Why is it that?
Because that way it changes on the transition, so it gets pulled in.
Well, even though these are getting filled in later, after, let's say, one of these sections is full, because these subshells are the biggest subshells, they have their own stability that kicks in this second level right here. So technically, they're not core electrons, but they end up behaving like core electrons, which means they don't behave like electrons. So usually these don't, they're not used for this reason. Okay. But in that transition metal, then sometimes you do have access to it. So chromium, for example, there's a +6, there's a hexavalent chromium, in which chromium gives up all of these electrons. Usually they're only going to give up these 2, but sometimes it will give up some of the B ones because it's not full. It hasn't reached these guys, so it's not fully stabilized. But by the time we get here, then this level of stability has been. And so they're not likely to let these electrons. But do keep in mind that those shells are available. Okay. We don't, the alpha principle tells us to fill them in this way. So the 3D doesn't get filled until after the 4S because it's higher energy. But the 3D is a 3 because it's available here. So in biology, they go over the octet rule a lot. You know, they have you do the Bohr model 2, 6, blah, blah, blah. And octet rule, 80 electrons, blah, blah. But 80 electrons really is safe because it only applies to the SMP sections, which is all right. But we do have these available. Okay. So sulfur, well, these guys right here, silicon, phosphorus, they have the, they're the 3p. And that means that 3D is available to fill in electrons. These can have more than 80 electrons because the 3D section is open. It's not used unless it's needed, but it's used. So when you look at structures with sulfur and phosphorus, you can end up with 10, 12 electrons. And that's not breaking any rules.
How the outer valence electrons?
Because there's space. If there's space to put those electrons in.
So that's the example you gave with the UTEP auditorium, kind of?
Yes. Mm-hmm. Now.
So there's space, it just doesn't mean they'll be there.
It doesn't mean, the seat is available, it doesn't mean that you sold it ticket. Sure. Basically, don't get hung up on the octet. The octet rule is more of a guideline than an actual rule. So because of off-bound, we fill this, and then this, and then we go back. But this section, you know, Ticket Master sells those tickets first before it sells these, or whatever reason. But these are available at that time. So you can have 2, 4, 6, 8. This is your octet row. But these seats are at the same level, they're there. So sulfur can put electrons there. Phosphorus can put electrons there. And you end up with structures like PCO5. In which phosphorus has 10 electrons. And it's not breaking up any rules. The rules are broken if there's nowhere to put the electrons in. Here, you cannot go beyond 8, period. And that's a rule that cannot be broken because those spaces are not available. But here, they're available. Okay, so you'll see sulfur with 5 or 6 atoms attached, which means 12 electrons, 10 electrons. But it has the spaces. So, now because we do concentrate on the SMP section, on the main group elements, and even if we do have this section there, these numbers are always less than this. So basically, this is what we consider the SMP sections. And that's 8 electrons. Those are your valence electrons, and those are the dots that we put in. So in the lowest dot structures, you have as many dots as you have valence electrons. So group 1 has 1 valence electron, 1 dot. Group 2 has 2 valence electrons, 2 dots. Group 3 valence electrons, 3 dots, although we have 2 electrons. Now, how we put those dots in, there's not really a rule. So magnesium's in group 2, 2 valence electrons, 2 dots. You can put them on any side of magnesium. Now, we do not pair them up until each side, and think of it as a box. until every side has at least one electron, then we can start pairing them up. And so elements in the same crew have the same pattern because they have the same number of valence electrons. Group 1 dot, group 6 dots. Notice up to carbon, there's a dot on each side. And then once we get to nitrogen, now we can pair them up. And then oxygen, 2 electrons are paired, 4 electrons paired. And then by the time we get to group 8, then 8 valence electrons. The SMP sections. And everything's full. Right electron dot symbols for each one of the following. Chlorine has 7 valence electrons, it's in group 7. One, two, three, 4, 5, 6, 7. And remember, it doesn't matter.
So even when it starts to pair, it doesn't have to go. I thought when it had to pair, it had to go like clockwise.
Can go clockwise, counterclockwise. Carbon 4, nitrogen 5, and once again it doesn't matter. So 1 with 1 electron, doesn't matter which side. 2, pick 2 sides. 3, pick 3 sides. 4, pick 4 sides. When you get to 5, then you have 1 pair, and then 3 by themselves. When you get to group 6, you're going to have 2 pairs. 2 by themselves. Group 7, 3 pairs. 3, 3, and then 1 by itself. That's what it's doing. So atomic size, the size of an atom. The size of an atom is determined by the atom's atomic radius. The distance between the nucleus and where we're likely to find the outermost electrons. So the electrons are always moving. So it doesn't really have an edge, but it's where we likely, where's the last place where we're likely to find that electron. Now, as we follow patterns on the periodic table, it increases for the group set of elements from top to bottom. And that goes back to the shells. So the nucleus is here, and then we filled in the first shell. So I need to put the next electron. Well, I have to go farther away. And then now that's full, and then I get further away. So now the second shell is full. And then once the second shell is full, I have to go to the third level. And then refill it up. But as every shell gets full, we have to go to the next one. And every time we go to the next one, we get further away from the nucleus. And this is the radius. Here, here. So as you go down the periodic table, it's getting bigger. So from top to bottom, the atomic radius increases. They get bigger. Those electrons get further away from the nucleus.
So it gets bigger because the electrons are getting further away.
every time we add a new shell, that shell, there's no room in closer. Going back to Ticketmaster. You know, when row 10 is full, we go to row 11.
It's just like how far you are away from the stage, right?
Farther away from the stage. Now, as we move from left to right, we're putting in those negative charges at the same distance. So as I start filling in that 3D section, as we're moving from left to right, and I start putting more electrons, that attraction to the nucleus increases. For every electron we add, we're adding a proton. That magnet, that attraction is getting stronger. So if the attraction increases, they get closer. If they get closer, it's shrinking. So the atomic radius decreases. As we move across the periodic table from left to right, we're adding electrons at the same shell. And for every electron, there's a positive, there's a proton attracted. The attraction increases, it shrinks. Okay? And then everything else below it also shrinks, so everything gets closer. So top to bottom, it increases, left to right,
It
it decreases.
that makes sense.
So smallest up here, and for purposes of this, hydrogen belongs here. Okay, hydrogen belongs here in group 7, right next to here. So hydrogen and helium are the smallest on the top right. On the bottom left, then we have the biggest atoms.
Atoms or the radius?
Both the atom,
It's equal.
It's the atom.
The atom itself.
That's atomic radius, not the nuclear radius. Questions? Now we have something called ionization energy. And we define ionization energy as the amount of energy needed to remove an electron from an atom. So to remove that electron, we're making a positive ion. And we see that happen. Now, there are actual energy values. So the rule says that they are calculated in the gas. So just plug in any symbol for X, and that's the equation for ionization energy.
Is that an LE or IE?
It's a 1E.
Oh.
So one electron. Okay.
Oh.
Because there's first ionization energies, your second, third, fourth, but we're only looking at the first one. So we're removing one electron. So the stronger that electron is attracted to the nucleus, the more energy that's needed to remove it. The weaker the attraction of the electron to the nucleus, then the less energy that's needed to remove it.
So it's opposite of the atomic radius.
So, from left to right, the radius decreases because the electrons are being attracted more. It shrinks because they're getting pulled in. Well, it's going to take more energy to take them out. So, because the attraction increases from left to right, the ionization energy increases from left to right. And as we go from top to bottom, remember we're putting them farther away, which means the attraction decreases. So, ionization energy decreases also. It's easier to remove. Now, as we go from left to right, we're getting closer to a full shell. And that's what elements want, full shells. from left to right, we start with the metals, and then as we get to the right, we get the non-metals. Yes. Since metals are furthest to the left, they only have a few electrons in that shell. It's barely starting to get full. They have no ionization energies. Your non-metals, they're closer to being full, so they don't want to give up electrons. That gets them further away from getting full. So they hold on to them stronger. So they have higher ionization energies. So the rule of thumb is that non-metals have higher ionization energies than your non-metals. So high ionization energies, low ionization energies. So increases, decreases.
Increases from left to right.
So non-metals, it's low and low is like opposite.
For ionization energy.
So the smaller the radius, the stronger the ionization energy is.
Yeah, remember how he's talking about the magnet? Remember the magnet behind here? Pulls it harder.
The stronger the attraction, the more you have to work to get them apart. And that arrow means left to right. Parts of it. And then notice this yellow part. It looks like the head of an arrow. And then that's exactly what it is. You have an arrow like this, where ionization energy increases.
Oh, that's what those things are.
Attraction increases.
On the periodic table you gave us, that's what those lines and arrows are. Ew.
That also follows the pattern. These are the non-metals. This is where the non-metals congregate. This is where the metals congregate. So that also has to do with metallic character. Metallic character decreases. As we move from left to right, then I get metalloids, then nonmetals, which means there's less likelihood that I'm a metal. From top to bottom, I start non-metal, then I get metalloids, then I get metals. So as you come down, the more likely you are to become a metal. So metallic character increases from top to bottom.
So it's similar to the atomic gradient.
Yes. Yes, it is.
On the power plant, it says decreases going down the group.
For,
Metallic character.
no, that's a type.
Okay.
Okay.
Let's see, element attackers, one that loses their incidents. Metallic characters with prevailing metals and lesser metals. It is less for non-metals, increases going down. No, increases going down.
On the next slide as well, correct?
Yeah, because on the next slide it says increases.
No, on my next slide says decreases.
On your
So
slide.
this is right.
Yeah,
This one, this
but
is,
the paragraph.
but this right here.
No, the next one, and then the paragraph it says decreases going from left to right. Never mind, sorry. Left to right, yeah, that's right.
And then, once again, just follow the pattern. Okay, if you're here, non-metal, metalloid, oh, now I get the metals. And so those become then the patterns. So let's see, given the elements carbon, nitrogen, and chlorine.
So chlorine would be the largest?
So let's see
Oh, no,
size.
wait.
So from left to right, it decreases. So we know carbon is bigger than nitrogen.
Yeah,
Okay, and as you go down, it increases.
yeah,
Okay, then we can expect chlorine then to be,
larger.
and it goes to the next shell. So the assumption is that once you make a jump on shells, then everything else in that shell will be bigger than anything else below.
Yeah,
The assumption, so we can expect chlorine to be the biggest.
okay. The highest in energy.
So the one that's will take more energy.
Is
to
carbon?
remove an electron. So from left to right, it increases. Okay, and then from top to bottom, it decreases.
Decreases.
Okay, and so we know nitrogen will be bigger than carbon, but because it increases here but decreases here, it becomes difficult to really know about chlorine, whether it's bigger than nitrogen or not. It turns out that it is. Okay. As it turns out, chlorine has one of the highest ionization energies.
So you can't really tell just by that assumption?
Right, because it increases as you make the left to right, but you're decreasing because you're top to bottom. Okay,
Yeah,
so
so
that
it just
one's
depends how much it decreases from top to bottom.
So chlorine would have the highest ionization too?
fluorine, yes. And then nitrogen is increased. Now, what's going to become important for the next chapter, okay, and it goes to this side. Elements that have low ionization energies, the ones that have the outermost electrons more weakly attracted, those elements are more likely to lose electrons and become positive ions. And those are your metals. So your metals end up liking to become positive charged particles. Your nonmetals, they hold on to electrons more tightly, they're closer to being full. So they don't like to give up electrons, they like to capture electrons. So when they gain electrons, they become negative. And your metals then end up wanting to become negative. Now, how much they like to give up and gain, it depends on how closer they are to getting full. So sodium, right? This is the electronic configuration for sodium. First shell is full, second shell is full. And then you have one electron by itself on that outermost shell. It's loaded. Okay, so it's attracted very weak. Sodium then has a choice. It can fill the whole third, it can fill up the whole third row, which means it needs to capture 7 electrons. Or it just gives that one up.
The boot.
If it gives this one up, everything is full. First shell is full, second shell is full. And that's what elements want. So group 1 elements, the group 1 metals, they always give up 1 electron
To be more stable.
because it reverts them to the full shells that they already have. And then it becomes a question of numbers in terms of the active rule. You know, you have that halfway point at 4. So 1, 2, and 3, group 1, group 2, group 3 metals, they will give up 1 electron, 2 electrons, 3 electrons respectively. Group 1's metals become +1, group 2 become +2, group 3 become +2. And now 4 is at the halfway point, so we skip 4. Now we go to the next section, group 5. Group 5 can gain 3 to fill up or lose 5 to revert back to the one that's full. Well, it's easier to move 3 than to move 5. So they will gain 3 and they become -3. So your non-metals in group 5 become -3. Group 6, gain 2 or lose 6, or gain 2 requires less effort. So your group 6 non-metals, gain 2 electrons, become -2, like oxygen, so oxygen is always -2. And then last but not least, your group 7, they only need 1 more. So they get 1, and they become -1. So fluorine, chlorine, bromine, iodine, they become -1 ions. And that's to reach that full shell stability. All right, so we'll leave it here, and then tomorrow's lab, which is the electronic configurations. And I'll have your test.
Okay.